Okay. So how come the rest didn't do? Is it because you don't understand? Is it because you're busy? Is it because of other reasons? Should we start the class already? Yeah, so that we can release everyone earlier. So today, this is what we are supposed to do. So we are supposed to discuss the results that you got from last week's homework. Then we want to do new things. So we want to learn new things. This week, what we are going to learn is polynomial regression, as what we discussed in last week's lecture. And then we want to discuss, we want to see how to do regularization. And we want to introduce another feature engineering technique called feature scaling. Okay, and we also explain why is this important. Okay, so, right. You just came in. Did you do last week's homework? Did you do last week's homework? Okay, noted. Okay, so now, assuming that you have already done last week's homework, this is the point that you are supposed to arrive at. Okay, so now we should have the last week's lab. We see how to build a baseline model LR01 using three features: engine size, cylinders, fuel consumptions. Yeah, and the point that we got to is R squared equals to 86%, and another R squared on test data set is 88%. Yeah. So now you're supposed to build another two models, LR02, which we take the similar three features, the three same features of the baseline, and we try to include four new additional columns, which is field type X, field type Z, field type E, field type D. So these features are all the one hot encoded field type features. Yeah, and we are supposed to also build another one, LR03, where we want to include the same features as what we use in the baseline model, the engine size, cylinders, and the fuel consumptions with the label encoded field type. Yeah. So now if you have already run the test and built the model, you will come to see that the R square for this model, LR03, is 88%, which is quite close to our baseline. And the R square of 89% on our test set, which is also quite close to our baseline. And the performance for LR02 seems to be better, which is 99% of R square, 99% of accuracy on train set, and 99% of accuracy on test set. Okay, so now based on this table, what can you conclude from here? Yes, one hot encoding seems to look the best because it helps the baseline model to describe our target variable a little bit better. Not a little bit, much more better. Okay, and the best model that we have so far is LR02. Okay, what if I ask you to comment on three of these models in terms of overfitting, underfitting, and good fit? We should be looking at all the R squares. Okay, so now if we look at the R square of the best model, 0.99 to 0.99. So this tells us, what does this tell us? Is it underfit, good fit, overfit? Should be a good fit. Yeah. how do we spot what if this model is overfit? What would you see? Correct. You will see probably 70 over or 80 over in the test R square. So that is the situation of overfit. Okay. So now based on the best model that we have so far, using the same set of features, how would you rate this model, LR01? Is it under, good, or over? Obviously under, right? But before we train LR02 and LR03, you wouldn't know that this 86% is actually under. We could be assuming that it is probably a good fit because it is explaining 80 over percent already, close to 90%. But it's just by having seen a better ones that we decide, oh, this is an underfit, which can be slightly better. Okay. So now, I'm not sure if you have tried to plot additional graphs. So right now, we have our models, we have our R squares. That means we have a set of predicted values and a set of actual values, right? So now what we can do here is to plot this graph out. Oh, by the way, this is a link to the sample solution of last week's homework, yeah? Okay, so now we have a set of actual value and the predicted value. If you were to plot them out by different model, this is what we are going to see. So now the blue color dots here refers to the actual values, okay, the actual Y value. And the red color dot here refers to the predicted values, okay. So all the graphs are the same, replicated the same way. Yeah, we just take a random X feature. So in this case, I'm taking the fuel consumption, and on our y-axis is our target, which is the carbon dioxide emission. Okay, so from LR01, we know that the R square is 86%, and this is how it looks like. What we wanted to observe here is that the predicted values is very far off from our actual values. Okay, so now there is error, high error or high bias between our predicted values and our actual values. Okay, so now similar observation is seen in LR03, where we see that a lot of the predicted values does not tie with the actual values. Yeah, the predictive power is just not as good. But when it comes to this LR02, we see that the predictive power is pretty high because the predicted values is very close to the actual values. That means this model has very low bias and high variance. Okay, understand now? Okay, so now based on the tree, we decided that, okay, LR01 is the one with the lowest bias and highest variance. So now what we want to observe here is, yes, around this range itself, we can see that the predictive power is very good because the points sort of overlaps between the predicted and the actual values. But around this area, we can see some gap and some bias between the predicted and also the actual values, right? So now, can we actually further reduce the bias around this area? Okay, that is what we are going to see today. Okay, this is the notebook to last week's solution. So then, in this case, what we are trying to do is to decrease bias, and therefore, what technique do we use today? Still remember this chart, right? So now say, for example, we are probably arriving at a stage of between here and here. Yeah, we have low bias, high variance. So now what we are trying to do is we want to reduce the bias further. Reduce the bias further. Therefore, we want to increase the model complexity. So in order to increase the model complexity, what are the techniques that we can use? we can include more and more features. We can manually input more and more features that would describe the relationship, or we can use polynomial regression, or we can train a neural network, which is more complex to capture this kind of, to reduce bias. Okay, so polynomial regression. So this polynomial regression is a technique to include more and more features into our regression model by creating new feature based on the current feature which we have. And the purpose of this polynomial regression is to help this multiple linear regression, which capture linear relationship and make an assumption that everything is linear, to capture non-linear relationship by adding multiple degree of polynomial function. Say, for example, if let's say we are adding a degree of 2, second degree of polynomial function, we are basically trying to build a quadratic model. And whenever we are building a third degree of polynomial function, it is probably a cubic model. Yeah. So these are the models that capture non-linear relationship. Okay, and when we take a lot of them and combine together, it may help us to describe the relationship between the features and our target variable better. Okay, so what we are trying to do here in practical is this. So assuming that you have already trained, you have already trained LR02 last week, this is what you will see. Okay, LR02 has 7 features. We are using the engine size, cylinder, and also fuel consumption, plus D, E, X, Z as our feature. These are the coefficient that comes along with all of these feature. This is our y-intercept. Okay, so this is LR02. So now when we include polynomial feature into this LR02, what it may look like is then we are adding in additional feature to the model. So what is included? What is added into this model? So now take a look at this. So now this first this 7 features, the original features, they still remain in the polynomial features. So now what are the new features which is added in, newly introduced into the model is the square of D. Another feature is D times E. Another feature here is D times X. Another feature is D times Z. Another feature is D times engine size. Then another feature is D times cylinder. Another feature is D times fuel consumption combustion. Then we have E square of E. Okay, E to the power of 2 square of E. EX, so far and so forth. So these are all the features that we included. And how do we decide what features to include here is the point of today's practical class. Okay, so now what we are trying to do here to build a polynomial regression is turning the original ones, the multiple linear regression, into polynomial regression. So how do we do that? So let's take a look. In order to train a polynomial regression, it is very easy. Yeah, it only takes 4 steps. So the first step here is to find out the best polynomial degree. Then, after finding the best polynomial degree, we'll train the model. After training the model, we'll then use the model to make prediction. After having the predicted values, we will then evaluate our model. Okay, so now how do we find out the best polynomial degree? How do we know that which polynomial degree best describes the relationship between our features and our target? That is a big question because initially we have done our EDA. We are only able to find out the relationship between a single feature and our target feature, right? Even if with our plot. What we couldn't find out here is what if the first feature and the second feature taken together, how does it describe our target variable? This is something that we couldn't find out from our univariate and also bivariate analysis. And therefore, we are going to do a trial and error. So we are going to do it over and over again, retrain and retrain again. So in order to do that, we are not doing it manually. Instead, we will introduce a function called grid search to automate this task for us. Yeah. So we are just doing a trial and error method to say we use this grid search to find out whether the first degree, second degree, or the third degree will be the best degree, which describes the relationship between our x features and our y target. Okay, so how do we do that? So first step here is to find the best polynomial degree using grid search. Yeah. So this is what we need. So we will first need grid search CV. We will need a pipeline, and we will need polynomial features. So now what do? We will be using this pipeline to package the polynomial features and linear regression, because we still want to maintain our linear regression. But right now, what we wanted to include into this linear regression are all the polynomial features. So now we will put polynomial features and linear regression into a pipeline. Okay, so these will be our model. Last week, we only do linear regression and put that into a variable, this small function. This time around, we were packaging polynomial feature and linear regression into a pipeline. Yeah. So then once we have a pipeline, we have a function, and our task here, the first task here is to find out the best polynomial degree. Therefore, we need to define the parameters that we want to find out. Say the normal range of polynomial features that we usually use is degree of 1 to 5. Yeah. So in this demonstration, I will optimize this using 1, 2, and 3. Okay. So we have our pipeline. We have our parameters that we want to optimize or find out the best. So now we will put the pipeline and the parameter into our grid search. Yeah. So here we are putting in the estimator, our pipeline, and the parameters into our grid search. Okay. So what happens here is that this is a function that instructs this environment or this computer to do a grid search. So what does it mean by grid search is it will do this linear regression with polynomial features first time with first degree. Then it will repeat the same thing, training another models with second degree. And then it will do the same thing here with third degree. Yeah, so it will repeat multiple times in order to decide which one is the best model. Okay. So now, other than that, it is doing 3 times. It is just not just doing 3 times, but in fact, we define here that we want the model, or we want this program to run this with 5-fold cross-validation, CV equals to KF. KF is the one that we have defined last week, if you still remember. K-fold cross-validation, where we define n splits equals to 5. Okay, so CV equals to K5. Yeah, so 5-fold cross-validation. So then this is a function which we want to save into a variable called LR02 polynomial. So once we have the function, we will feed it to our X train and Y train. Once we feed it to our X train and Y train, we are having all the models saved into our LR02 poly. Yeah. So once we have all the models with its scores and also the features, we are then able to call out the model which produce the best score, and also what are the parameters of this model that gives us the best score. Okay, so now once we run this, we are going to get this value here, which is the model with the best score of the best model. Okay, we can see that the accuracy is somewhere about 100%. And the polynomial feature degree of this model is degree of 2. Okay, so now suggested by this function itself, second degree is the best degree. So what do we do next is we find out the best polynomial degree. So next what we are going to do is to train a model using the best parameter. So now we know that the best parameter is 2. So then we define that, okay, polynomial features that we wanted now is degree of 2. Then we save into PF. How do we fit the model? We will then use the pipeline again. So now we will take the linear regression and put into the pipeline. And this time, instead of polynomial features of unknown features, we will put in, make higher degree, a known polynomial feature, which is a degree of 2 into the pipeline. So now say this pipeline is trying to define a linear regression with second degree of polynomial function. Yeah, so we save it as LR02 poly 2. So now once we have this function, we are then fitting this function to our X train and Y train to get our model. So once we have our model, we can take a look at the score, which is the R square. So another part about this model is then we want to know what are the model parameters. Okay, so what is the model parameters in regression? The y-intercepts and the coefficients. Yeah. So now we are going to read the model parameters. So now all the features in this polynomial regression is something that are included. Yeah. We added in new features, and therefore, how do we call them out? So we want to take a look at what features are included and what are their coefficients respectively. So now we are going to call this LR02 poly 2, and then we use the get features name out to get all the features that we have included. So then we will use the coef, the same function that we have used before, to call out the coefficients, and we are putting them into data frame. Then we will use the intercept function here to call out the intercept. And once we run this, we are going to get this result, which tells us how big or how small our model is about. So if you still remember at this stage, we should be able to write the equation of our model, which is y equals to 0.21 plus so far and so forth, right? It will be a little bit too long for us to write it out, and therefore in this sense, we do not write out in the case where we build a polynomial feature. But if we are told to provide we are asked on what features is included, what are the coefficients, this is what we should provide. Okay. So now this gives us a look at a peek into what are the features in this model and what are the coefficients for each of the model and y-intercept. Yeah. So now once we fit the model, we read all the model parameters. That's it. And now we want to use this model that we built to make prediction and evaluate the model. Okay. So in order to do prediction, it is very simple. So now we will take back the same model, LR02 poly 2, predict on the features in our X2 test and produce a set of predicted values, a predicted y-test value. Yeah. So now once we have the predicted y-test value, we are going to use it to compare against our actual y-test value and compute the MAE, MSE, RMSE, and R-square score. Okay, so you can see that this process repeats over and over again for every single model that we build, because this is just how we evaluate the performance of our model. Okay, so then this is the results. So now, if you still remember, our first model that we built, LR01, has an MAE of 16, correct? We mentioned that it is somewhere around 16. And so now with this polynomial regression, we are reducing the MAE to 0.26. So now they are even closer between the predicted and also our actual values. Yeah, and the R-square score is improved from 86% to 100%. So if you were to plot the difference between the actual value and the predicted value, this is what we see. So now it is further improved. So before we started the polynomial regression, this is what we have. So now we have our LR02, which we still see some gap or some bias around these values. But right now, after adding in the polynomial feature, we are further improving the model which are already having good predictive power. Okay, so this is the point that we get to at this point. Yeah, any question? This is not the end. So at this point, what would be our concern? Yep. We should be worried about whether this model overfit or not, and whether this model is able to generalize to future unseen data when we deploy this into the actual world or not. So now what are we trying? What should we do next? If we are worried of overfitting with the too complex model, so now what we wanted to do is to push it backwards, and therefore we want to introduce some bias or reduce the model complexity. Okay, and how do we do that? We can, to simplify the model means we can remove some features, or we can just use a smarter way of doing it, which is regularizing it. Okay, regularizing it. So now let's see how to regularize this model. Okay, so now we move from LR02 to LR02 plus polynomial features. And now we are trying to regularize these polynomial features using regularization. So recap, regularization is trying to increase or decrease bias. Increase bias. Okay, increase bias. Increase bias because we mentioned in the lecture that what happens during regularization is we are adding some penalty term to our cost function. So, and in this penalty term here, we have to find out the optimum or the best regularization strength parameter called lambda. So a higher lambda will result in a simpler model with more bias, but a lower lambda here will maintain the model complexity with more variance. Okay, so let's take a look. And in the lecture, we also mentioned that this regularization, we can also use this regularization for feature selection, right? So it is also a way of helping us to select the important features, shrink all the unimportant features and magnify the important features. So now take a look at these two sets of values over here. So now on the left here, what you see is the features and coefficient of the polynomial features. And on the right is regularized version of this model. Do you see the difference? We mentioned that this regularization can help us with feature selection. But now what we see here is that the 36 features here on the unregularized model, so the number of features between the two models remains the same. Both of them have 36 features. Okay, so now what is different here is certain features in the regularized model is now reduced to 0. So this is a way of how this regularization helps us to shrink the effect of unimportant features as a form of feature selection. not really excluding them, but shrinking the coefficient to 0. And therefore, whenever it comes to that coefficient, the effect is 0 because we are having a coefficient of 0. Okay? Understand? Huh? So now, in order to find out this best regularization strength lambda, we are, again, it takes a lot of experiments to trial and error because we will never know which one is the best. And therefore, we will do it using the grid search as well as validate it using cross-validation. So now, it will take the similar 4 steps here as what we have seen in polynomial regression. But instead, the first step is slightly different. Instead of finding out the best polynomial feature, we want to find out the best regularization strength using grid search. So once we find out the best regularization strength, what we're going to do is to train the model and make prediction using the model and evaluate the model. Okay, we are repeating the same steps. So now in order to find out the best regularization strength, we will make use of the grid search. So we will also create a pipeline, but now we need an additional step, which is scaling the data. So what does scaling the data mean here? Okay, so now this is a type of feature engineering technique that we want to introduce today. Okay, so scaling the data means changing the scale of the features. Yeah, scale of the value of the feature. So feature scaling, it is another type of feature engineering technique. We have covered feature encoding previously, and now we want to cover another type, which is called feature scaling. So feature scaling works by transforming the data into same scale. Let's take a look at how to do this. So now, in order to scale the values, there are 3 algorithms which are commonly used. Of course, there are more of them, and these are the 3 basic ones that we should know. So we have min-max scaler, we have standard scaler, and we have robust scaler. So each of them differ by the way of retabulating our x values. So let's take a look at the first one, which is the standard scaler. So in standard scaler, how we want to get the new x is we are taking the original x value minus of the average of all the values in the same feature. Then we divide it by the standard deviation to get the new value. Okay, so this is what it means. And let's see what is the effect of standard scaling. So now let's take a look at this example. Say, for example, we have 3 features over here. The first feature is annuity amount that range from 0 to 250,000. Another one is goods price, which has a range of 0 to 4 million. Then another feature here is days of birth, which range from 20 to 70. So now we can see that, okay, the minimum value seems to be quite close together from 0 to 20 across different features. But the maximum value here has a very large gap. For example, we are seeing 250,000 to 4 million to 70. So the range is very big. The impact of this is if we were to include this feature into multiple linear regression like directly, our algorithm is going to focus on the feature which has the highest value, regardless of what it is, because that is what it sees. It sees it, it assumes it based on the value that it sees. Okay, so now what we are going to do that to try to make this algorithm treat every single feature equally is then to scale them. So now, once we apply this formula, taking the original x minus of the average divided by the standard deviation here is, we are trying to change the range of this annuity amount from 0 to 250,000 into a range of -2 to 15. So now we are changing this goods price from 0 to 4 million into a range of -2 to 10. And then the days of birth, we are changing the range from 20 to 70 into a range of -2 to 2. Okay, so now when we compare the minimum value between the 3 features, we can see that they are more or less the same. And the biggest impact happens to the maximum value of 3 of this feature. So now we can see that instead of 250K, 4 million and 70, now the maximum value of the three features are very close together, which are 15, 10, and 2. Okay? So this is the effect of scaling. So now let's see, for example, another type of scaling, which is min-max scalar. So the way of computing this the new value of x is slightly different. We make use of the minimum and maximum instead of the average values. So now what we are trying to do here is take the original x here minus of the minimum x divided by the range of the minimum and maximum value. And therefore, it will give us a new range, and all of the feature will sit within 0 to 1 because we are taking and standardizing it using the minimum and maximum value of each feature. Okay, so now all of these feature will then be sitting within 0 to 1. So now what happens here, if we were to include all of these features into our multiple linear regression model itself, now the model can treat every single feature very equally because they are within the same range. The minimum and maximum of all features are within the same range. Okay? So robust scalar is just another type of scaling method where instead of using it is quite similar to the standard scalar, but instead of using the average and the standard deviation, what we are using here is the median value and the interquartile range. So instead of this x minus mean divided by standard deviation, we are taking x minus median divided by interquartile range. Okay, so the impact or the effect is similar. So right now we are changing the values here into another range which has a closer minimum and maximum values between three features. Okay, so this is transformation. Yeah. So now after this scaling, what we should notice here is we are changing the scale of the minimum and maximum value for each features only. We do not change the way of how the data is distributed. Yeah. So now that is another technique which we don't cover today. It could be a bit too much. We'll take some other time to do this. Data transformation. So data transformation is to transform skewed distribution into normal distribution. Yeah. So now let's get back to our regularization. So we will need to scale all the features for regularization so that we are treating all of the features with similar weights. Because right now what we're trying to do is to regularize the model. Okay, so in order to do regularization, in order to find out the best regularization strength, we will need grid search, our standard scalar. So in this demonstration, I will do standard scalar. In the case where you want to experiment on min-max scaling or robust scaling, you have to import the min-max scalar and also the robust scalar here. Okay, so now we want to use the regularization function instead of the linear regression function. Therefore, we have to import lasso and reach. Yeah. So lasso and reach, they are also linear regression function, but they differ from linear regression function in terms of their cost function. So when the cost function is different, we have to create a new packages. Yeah. So we have to import new package, which is lasso and reach. So we will take the same step. We will put the standard scalar into our pipeline. We will put our polynomial features into our pipeline. We will put our lasso into our pipeline. Yeah, because we know that our base model now is a LR02 with polynomial function. Yeah, second degree of polynomial function. So we have to also include this polynomial feature and lasso. Okay, so now let's just see that the next step here is to define the parameters. So let's just redo the polynomial features degree optimization. It should return us the same results. Then now we also want to regularize, find out the best regularization strength. So in order to find out the best one, we will normally define a range. Say for example, this time we will use 0.0001, 0.001, 0.05, 0.1, and 1, and find out the best regularization strength. So now the regularization strength, which is lambda, is usually called referred to as alpha in our scikit-learn package. Don't ask me why, because I also don't know the reason. Yeah, but they are just called alpha in the scikit-learn package. So once we have our pipeline and our parameter, we will package this pipeline and parameter into our research and say we want to do this for 5-fold cross-validation. So what happens here in this grid search is we are trying to say that, okay, so now we have two parameters to optimize. So train a lot of model. So first time here, use first degree with 0.0001 as your regularization strength. Second time, use first degree 0.001 as the regularization strength. Third time, use this and this combination. Fourth time, use this and this combination. Repeats for all the combination of our parameters, of the parameters that we define. So it will just repeat again and again and again at the back end to create multiple models. And every single model will be 5-fold cross-validated. Okay, and then it saves all of the model and all of the parameters within the function that we are fitting to our training at training X train and Y train. Okay, so now once we have this results, what we are going to do here is to call out the model with the best score and the best parameter that is tied to the best model that exists. So now let's retrieve the result. So once we run this, we are going to get these values. So this value is the score that is provided by the best model that it has trained. Yeah. So then the lasso regression alpha of that particular best model is 0.001. And the best polynomial, the polynomial feature of that best model is degree of 2. It seems like it is the combination of 2 and 0.001. Okay. So now once we know what are the best feature, we'll repeat the same thing, that is to train this model. Yeah. So we'll define a pipeline of this model itself where we want to remain the standard scalar. Now we want to define our polynomial feature, which is a degree of 2. Then we want to use train it using lasso regression instead of linear regression. So lasso regression here should have an alpha or the regularization strength of 0.001. Okay, so then we put this pipeline into a variable, and this variable is a function. We will fit this function to our X train and Y train to produce our model. So now once we have the model, this model comes with its model parameters. So what we are trying to do here next is to read all the parameters. So all the parameters here refers to every single feature that we use to train the model itself and its coefficient, or the beta 1 to beta n, and the intercept of the model itself. So once we read all the model parameters, we will then use this model to make prediction. So we will take the model, make prediction of the Y value using the X2 test features to produce a set of predicted Y values. Once we have the Y values, we are going to compare the predicted Y values to our actual Y values. So once we compare the difference between the predicted and the actual value, we are going to calculate the mean absolute error, mean squared error, root mean squared error, and also our R squared. Yeah, so this will reflect the performance of our new model. So this is the result of our new model. And when we tabulate the actual value and the predicted value, we can see that, oh, this model is actually regularized, but it does not impact its predictive power that we have seen earlier. Okay. And that is the end of training a regression model. Yeah. So now, in order to arrive at this point, we started off with our LR02, which was one of the best decided based on our manual feature selection. We manually select all the features that would best describe the relationship between our feature X and our target Y. Then we use this as a base and include polynomial features. We find out the best polynomial degree that describes the relationship between our X feature and our Y. Then we train a polynomial regression that gives us this one. So, and then followed by, we are worried whether this model would overfit, will be overtrained or not. So then we take this model and regularize it to make sure that this model is generalizable to future unseen data, which is good for deployment purpose. And now at this stage, what we wanted to try to prove is that, okay, we have regularized it, and this model should be able to generalize, and it does not impact the predictive power. That's the end of regression. Yeah, I hope you learned something new. Is there any question? Sounds good. Okay. So your midterm tabs will cover everything from EDA to this stage. Yeah. Good. Very fun, right? It is fun. So you can ask me if you have any question. Otherwise, we shall dismiss, and I'll see you tomorrow.
Bye-bye.